Welcome to the third lecture of Module 7. Today we're going to be talking about the factorization method. This will be the subject of the next two lectures that we have. This is the way we generalize what we did for the simple harmonic oscillator to be able to solve any problem in quantum mechanics that can be analytically solved. So interestingly, the factorization method was developed by Schrodinger, who also created the Schrodinger equation. It was developed about 15 years after he developed the Schrodinger equation in 1940 to 1941. This is during World War II, and Schrodinger spent World War II in Ireland. He devised an algebraic method to solve general quantum problems. This is similar to some of the techniques we've used before, but here we're going to develop essentially a cookbook method to do this. Or if you like, we're going to discuss how it's done in its most general fashion. This method can solve all known analytically solvable quantum problems. Extending it to work numerically for the arbitrary quantum problem is actually still an open problem. There is no set way in which to do that just yet. There are 10 steps or 10 important points that I want to establish when we use this method for solving bound states. There's only one for the continuum states. And so this will be heavily weighted to looking at bound states. Bound states are states that have energy that is less than the maximum of the potential, and these bound state energies tend to be localized in some region in space, and the system does not move all the way out to infinity when it's in a bound state. All right, the first thing in Schrodinger's method is working with what is called a factorization chain that creates a series of auxiliary Hamiltonians, H sub I, that we use in solving the original problem that we want to solve. So we start with our original Hamiltonian H, which I'm going to be calling H sub 0, and then we form these raising and lowering operators, A dagger 0, A0 plus E0. We need to be able to factorize the Hamiltonian into this form, and we're going to discuss a bit more about exactly how that's done as we go through this list. But once we've had that, then the next thing that we do is we define an H1 by switching the order of the A0 dagger and the A0. So it's going to be A0, A0 dagger. We're going to call that H1, and then we're going to take that Hamiltonian, which has its own potential. It's a different potential usually than the H0 had. And then we need to find a way to factorize that problem. When we factorize it, we're going to call it A1 dagger A1, and then the energy might change. That value E1 might change, so we call it plus E1. And then we just repeat this. H2 will be changing the order of the A1 dagger, so it'll be A1 dagger plus E1. We then refactorize that Hamiltonian, and we get into an A2 dagger A2 plus E2. And then we continue, we do the same thing for H3, and we keep going. And the general case will have HI plus 1 is equal to AI, A dagger I plus EI, which is going to then be refactorized into A dagger I plus 1, AI plus EI plus 1. Now, the key to making this whole approach work is figuring out those factorizations for the next auxiliary Hamiltonian. And in general, that's highly non-trivial. But there's a large class of potentials called shape invariant potentials, where the same ansatz that you use to factorize H0 is the ansatz you use to factorize all of the auxiliary Hamiltonians. And so when you have that situation, this actually ends up being a fairly easy and fairly straightforward procedure. And it turns out all of the analytically solvable problems fall into this category, and so they can be solved in this fashion. But for now, let's just assume that we can do it, and let's see what happens under the assumption that this can be done. The first thing we're going to determine is the intertwining relation. You may remember that we determined this for the simple harmonic oscillator when we were looking at solving that algebraically, and I'm just reminding you about the definitions of the HI and the HI plus 1. So the intertwining relation essentially is having us move the auxiliary Hamiltonian past an auxiliary raising operator. So we start off with an HI AI dagger, and we want to move the AI dagger to the left through the HI, And we want to see what we get. And the claim is when you do that, you get hi plus 1 sitting on the right-hand side. That is by no means obvious, but the proof actually only takes a couple of lines. So let's go through it. So we start off just by plugging in the definitions. I'm going to plug in what hi is. You can see it there on the upper part of the page. It's just ai dagger ai plus ei, and that's multiplied on the right by the ai dagger. We now bring all terms inside the parenthesis, and I'm going to actually just switch the order of the second term, moving the ai dagger to the left-hand side. I can do that because ei is a number. And now you see I have an ai dagger on the left-hand side of both terms. So I'm going to factor that ai dagger out, and I'm left with ai dagger plus ei. But that's one of our Hamiltonians. We just look up and we see that is hi plus 1. And so we have now verified the intertwining relationship. And this is a very important relationship. We determine what the eigenstates are from this intertwining relationship, which is something we're going to do momentarily. Before we do that, we want to actually find out what the ground state is of each of these auxiliary Hamiltonians. So again, let me remind you what the auxiliary Hamiltonian is. It's written as ai dagger ai plus ei. And its ground state satisfies what's called the subsidiary condition. And that is that the lowering operator acting on phi I is equal to 0. We're going to use phi to denote the auxiliary Hamiltonian ground states. We're going to use psi to denote the ground and excited state of the Hamiltonian that we care about. Now, it's not obvious that this is what is satisfied by the ground state at this stage. But again, the proof turns out to be very easy, and we've seen it already before. The energy of the auxiliary ground state is going to be ei, and we're going to choose the auxiliary ground state wave vector to be normalized. And so bra phi I ket phi I is always equal to 1. Now, the proof that this is the ground state simply follows from the fact that this operator, ai dagger ai, is a positive semi-definite operator. And we can see that very easily because if I take the expectation value of that with any state, chi, I put bra chi ket chi on the other side, you can see that that object is going to just be the norm of ai acting on the state chi. And so because that's the norm, a norm is always a positive semi-definite object. That's essentially how the proof works. So we're going to go through it in detail. So the claim is that that operator, ai dagger ai, has as its smallest eigenvalue, or its smallest expectation value, is going to be 0. And it will be exactly 0 if ai acting on phi I is equal to 0. Because then when I take the norm of that, I'm taking the norm of the 0 state, and that's, of course, equal to 0. Now, if that holds, and of course that is the minimal state because we can't have anything with higher energy than that. Now, if that holds, when I evaluate the energy, you see if I operate hi onto that state, ai will act on phi I. That's going to give me 0. That gets rid of the first term, and I'm just left with ei times phi I. Of course, that's an eigenvalue-eigenvector relationship because ei is a number. And so we've just shown that the subsidiary condition guarantees that we have a ground state of the ith auxiliary Hamiltonian. This is exactly what we did with the simple harmonic oscillator. All right, now we can use that fact to get all of the energy eigenstates of our original Hamiltonian. And I'm simply going to claim that those excited states are given by A1 dagger, A2 dagger, A3 dagger, all the way out to AI minus 1 dagger acting on phi I. Now, for this, we definitely need to prove it because it doesn't look obvious. So let's act our original Hamiltonian. Recall that is H0 in our factorization chains. We're going to act that on the psi I. Let's write out what the psi I is in terms of the AI daggers. And now we're going to do intertwining. Recognize here, I have an H0 with an A1 dagger next to it. I can do intertwining and bring that H0 to the right-hand side, but when I do it, it changes into a H1. And now the H1, A2 is primed for intertwining, so I move that by and I get A2 dagger, H2. And now the H2, A3 is primed. I move that through, I get the H3, and I keep going all the way down the chain until I get all the way to the end where it's an HI acting on phi I. But phi I was the ground state of HI, so we know that that's an eigenstate. So I can just replace that by EI using the fact that it's an eigenstate. Now, EI is a number. I can just take that all the way to the left, and then I simply have to recognize that those set of operators acting on the state phi I is just the original state psi I. And we've figured out now that it is an energy eigenstate, and it's the ith excited energy eigenstate corresponding to this particular factorization chain. Our next step is to show that the energy eigenvalues form an increasing series. That means there's no degeneracy for any problem that is solved as bound states with a factorization chain. The way to do that first requires us to establish that the I plus first lowering operator is not equal to the ith raising operator. Now, it's very tempting from the way that we form this factorization chain, because hi plus 1 is equal to ai dagger plus ei. It's very tempting to say, oh, well, that's easy to factorize. Let me take ai plus 1 equal to ai dagger. Then I don't have to do any work. I've immediately done the factorization. But it turns out if we do this, then the factorization terminates at the ith step, so that there is no I plus first step if we do this. So to show why this occurs, recall that we form the I plus first state, psi I plus 1, from A1 dagger, A2 dagger, A3 dagger, all the way out to AI dagger acting on phi I plus 1. But this state will be 0 if I chose AI plus 1 equals AI dagger, because the subsidiary condition is that AI phi I plus 1 is equal to 0. And then if I replace AI plus 1 by AI dagger, you see then that AI dagger acting on phi I plus 1 is 0. But now look at psi I plus 1. That's the first operator hitting phi I plus 1. That means that's 0. That means all the other operators it's going to be 0 as well. And so we find that psi I plus 1 is 0. I have no next excited state. Now, you may think that this can never happen, but it actually turns out that there's some potentials where this does happen. These are potentials that have a finite number of bound states. When you solve them with a factorization chain, it turns out that this occurs when I can no longer get another bound state in my problem. So what this means is that the chain will terminate if we choose AI plus 1 equals AI dagger, so we can't do that. And that means we can assume that that doesn't happen. So we're going to assume that the AI does not equal the AI dagger. But in reality, the most important thing that we need to assume is that the AI dagger acting on the phi I plus 1 is not equal to 0. You're going to see why we need that in order to make the proof. And of course, if AI dagger acting on phi I plus 1 is equal to 0, then I don't have a state. And so that assumption must hold, even if we don't choose AI plus 1 equals AI dagger. We must always have AI dagger acting on phi I plus 1 is not 0. All right, so that is all we need to verify that the energy eigenvalues are increasing. And let me show you how that works. So I'm just illustrating for you here exactly what that chain is. The argument comes simply by calculating the expectation value of the ith Hamiltonian in this state phi I plus 1. Now remember, phi I plus 1 is an eigenstate of hi plus 1, and phi I plus 1 is a normalized state, so that's just equal to ei plus 1. All right, now let's rewrite that hi plus 1 according to the factorization chain. We're taking the first condition, ai dagger plus ei, and now what you see is I can separate out the two terms. The ei term is going to just equal ei because phi I plus 1 is a normalized ket. And now you can see, look, this is a positive semi-definite operator. That's the norm of ai dagger acting on phi I plus 1. But the norm must be greater than or equal to 0. But you see here, it can't be equal to 0 because we said ai dagger phi I plus 1 is not 0. And the only time that the norm is equal to 0 is if I have the 0 vector. And so we know that that second term is bigger than 0. Well, that's enough to tell us that ei plus 1 is bigger than ei. And then that establishes this result, that we have a increasing sequence of the energy eigenvalues. All right, you see that was actually pretty simple. All right, next thing I want to show you is that the superpotential is real. We're already halfway through the results I want to show you for the bound states. We're going to write the ladder operators in what is a standard form. This comes from a field called supersymmetric quantum mechanics. We're not going to talk about that in any great detail, but we are going to use some of their notation. We write the AI operator in the following form: 1 over the square root of 2m p hat minus I h bar ki wi of ki prime x hat. You see here x hat is an operator. It's inside a function wi. Ki and ki prime are wave numbers, which means that they have dimensions of 1 over length. And the function wi is called the superpotential. And when we use those wave numbers having dimensions of inverse length, that means that the superpotential's argument and the superpotential are both dimensionless. How do I see that? Well, look, that operator inside the parenthesis has the dimensions of momentum. But h bar k, if k is 1 over a length, also has dimensions of momentum, because h bar has dimensions of momentum times length. And that means wi must be dimensionless, because I have to add things together that have the same dimension. Now, I'm going to show you that this superpotential must be a real valued function, w. And what that means in the operator sense is that w of k prime x dagger is equal to w of k prime x. In other words, the w is Hermitian. Now, we're going to do this proof by schematically writing h bar k w k prime x is equal to B operator plus IC operator, with B and C both Hermitian. You see, in order for W to be Hermitian, C must be 0. Because otherwise, W dagger would equal B minus IC, and that's not the same as W. All right, how do we prove it? We just substitute in the definition. Now, I'm being schematic here and dropping a number of the constants because they just get into the way. And so schematically, the A operator looks like P minus IB plus C. You see, if I plug in for that W, a B plus IC, I get a minus I times an I for the C, and I get a minus I times the B. Now, when I take the dagger of that to get a dagger, because the B and C are Hermitian, that becomes P plus IB plus C. Okay? Now we just multiply these things out. All right? Let me maybe talk you through this first. You know, I have a P with a P, that gives me a P squared. I'm going to have a P with an IB, but you see there's a minus sign there, so I'm going to get a commutator of a P with the IB. I'm similarly going to get a commutator of the C operator with the IB. When I look at the C operator with itself, that's going to be squared. And when I look at the P operator with the C, you see those both have the same side, so I'm going to get an anti-commutator. I'll get PC plus CP. And you see there, so I get P squared plus PC plus CP plus C squared plus I, the commutator of B with P plus C plus B squared. All right? It's very simple algebra, and it really should take you no more than about 10 seconds to verify that. But here's the key. Our Hamiltonians aren't linear in P. The coefficient of the P term has to be 0. That isn't a commutator there, it's an anti-commutator. So there's no reason in the world to believe that that thing would be 0. Indeed, in general, it's not 0. The only way to guarantee that is 0 is if I take C equals 0. If I take C equals 0, you see I have a term that goes like P squared, and then the rest of the terms are functions of x, because B is a function of x, and the commutator of P with a function of x is a function of x. And so I then get it in the standard canonical form of the Hamiltonians we've been working with, which is P squared plus some function of x, which is the potential for the problem. And so from this reasoning, we learn that the superpotential is real. Now, there actually are cases where Hamiltonians do have linear terms. That happens when we couple our particle to a vector potential, meaning that we have magnetic or electric fields or both in the problem. We're not going to actually be talking about that in this class because we're not going to have time to talk about that in this class. But in that case, you could have an imaginary part to your superpotential. But in the cases that we're looking at, we don't have that. And so our function W is going to be a real valued function. Now, the next thing I want to tell you is that factorization is not unique. There may be more than one factorization chain. We already saw that with the simple harmonic oscillator, where we saw that we had one factorization chain that got us all the eigenvalues, and we had another one that gave us just the eigenvalues corresponding to the odd functions. Nothing in this procedure guarantees uniqueness, and we do have counterexamples like the one that I just showed you, so it's definitely not true. That then brings up the question, if I do and I solve a problem with factorization, you know, how am I going to know that I have all of the solutions? Well, that's going to be our 10th point that we're going to get to in just a bit. But right now we're going to talk about what happens when the wave function has a node. Remember, a node is a point where the wave function is equal to 0, and our claim is that when that happens, the superpotential diverges. So we're going to do this proof for the auxiliary ground state wave function, which we get by just taking the bra x multiplying the ket phi I. What happens when that vanishes? Well, we're going to use the subsidiary condition, which is A operator acting on phi I equals 0. Remember, the A operator is P minus I h bar kW. So I can rearrange the subsidiary condition to be P acting on phi hat is equal to I h bar kW of k prime x hat acting on phi I. Now let me multiply both sides of this with the ket x. I can't do anything with the left-hand side, but the right-hand side, I can let w of k prime x hat act on that because the state x is an eigenfunction of the operator x hat. I can just replace x hat by its eigenvalue, which is x. And so the w of k prime x is going to factor out, and then I'm left with the bra x ket phi I. That's just phi I of x. And so we can actually rearrange this into the form w of k prime x is equal to xp phi I divided by ih bar k phi I of x. All right, I hope you see what's going to be happening here. The superpotential must diverge when the auxiliary ground state vanishes unless xp phi I is equal to 0 at the same point where phi I of x is equal to 0. And we're going to show you now that that can't happen. So our claim is that we cannot have both of these equal to 0, because if we did, then the wave function phi I of x will be 0 for all x. We do this by showing that all of the expectation value of all of the powers of p to the n would be 0 if both x phi I and x p hat phi I are equal to 0. Now, I'm not going to do the full proof, but you'll get the flavor of it from what we're doing. Let's first look at the case with p squared. Now, remember, I can write p squared in terms of the Hamiltonian. I can write it as ei minus v auxiliary of x multiplied by 2m. Please pause the video and write this down. It's a one-liner if you don't remember it. Remember, the Hamiltonian is p squared over 2m plus v auxiliary of x, and we have the equation that h acting on phi I is equal to ei times phi I, because phi I is the ground state of the ith auxiliary Hamiltonian. Okay? Now, this is very simple. I just operate v auxiliary against the x eigenstate to the left. It becomes a function. I pull it out, and you see I get 2m ei minus vi auxiliary of x times x phi I. Well, if x phi I is equal to 0, then expectation value of p squared is also equal to 0. Now let's take a look at p cubed. Here, I can only replace p squared by 2m ei minus vi auxiliary of x if it's the p squared that's acting on the phi I that I can replace by that, because I use the eigenvalue eigenvector relationship for the Hamiltonian in order to get that. That means I have the p hat operator to the left. But that's no problem. In the case of ei, I can just pull the ei out, and that gives me the expectation value xp phi I. For the vi auxiliary of x, I'm going to move the p through on the other side by using an add 0 trick and replace, and then I'm left with a commutator. And so I can pull out that same factor times xp phi I plus 2mx commutator of p with vi auxiliary of x. Now, the commutator of p with a function of x is a function of x, because the commutator of p with x is equal to ih bar. And we already verified commutator of p with x to the n is equal to ih bar n times x to the n minus 1, and there's an extra minus sign as well. And so that's all that we need in order to verify that the commutator of p with any function v auxiliary of x is equal to a function of x. That means I can pull that out, and I'm going to then get x phi I, or the wave function. You can see if both xp phi I and x phi I are equal to 0, then the expectation value of the third power of momentum is also equal to 0. And then you can just continue doing this for higher and higher orders. I think it's fairly clear that you can see that this is going to work, and we're going to be able to ultimately get that all of the moments p hat of n are equal to 0. Now, if all of them are equal to 0, how do I know then that phi I of x is equal to 0? Well, let's assume the point at which both x phi I and xp phi I was equal to 0 was at the point x equals x0. Then I just say that the wave function at x is equal to the translation of x0 to x acting on phi I. That translation operator I can re-express as a sum over powers of the p operator. And so if all of the moments, all of those p hat to the n expectation values are equal to 0, then I just get 0 when I evaluate that. And so indeed, you would find very quickly that phi I of x is equal to 0. So this is just summarizing what I just said. All right, we're on to our 9th point. This says that the superpotential is continuous even if the potential is not continuous. There's a whole set of problems we haven't gotten to yet that are called particle in a box problems, particularly particles in finite square wells. And those are potentials that are discontinuous. And so suppose that we just happen to have a potential that is discontinuous at some point x equals x0. Now there's a requirement in quantum mechanics that the probability density and the probability current are both continuous functions. And this says in our language that psi x0 psi, that's the probability density, it's mod psi of x quantity squared, and psi x0 p hat psi must both be continuous. The second one is the probability current density, and I have not told you how we get that just yet. But because those two are required to be continuous, we just divide the second one by the first one, and you see that that then becomes the ratio of x0 p phi I over x0 phi I. And we already calculated that. That's equal to w of k hat x at the point x equals x0. And so if phi I x0 is equal to, if that ratio is continuous, that means that the superpotential must be continuous at that point. And so even if the potential is discontinuous, the superpotential is always continuous. In fact, we're going to use that fact to solve particle and finite square well problems. All right, the last one that we have for bound states tells us how we know that we have all of the states that we're interested in. It's the node theorem, and it tells us that we have all of the solutions. Let me remind you again, a node is a point where the wave function vanishes, and it turns out for all one-dimensional systems and all radial problems that we're going to be working with in higher dimensions that come from central potentials, the ground state has no nodes, and the number of nodes increases by 1 for each higher energy excited state. And what that means is I can tell you which excited state I have simply by counting the number of nodes that I have in the wave function, but it also allows me to tell whether or not I have all of the wave functions. If I have all of the nodes starting from 0 up to infinity, then I have all of the wave functions. So we already saw that this was the case for the particle on a circle and for the simple harmonic oscillator. In particular, we looked at the wave functions for the simple harmonic oscillator, and we saw that every time we increased the index by 1, that Hermite polynomial had an extra 0 in it, so we had another node entering into our wave function. We're going to prove this in class next week, and so I'm not going to say much more about this here, because we're going to be working on that again in just a bit. But I will just summarize that using it is how we can tell that we have all of the states with the right number of nodes, and then that verifies that we have all of the solutions for the problem that we're trying to solve. All right, now on to the continuum. Continuum solutions do not have factorization chains. They actually are solved by a single factorization. Now, we already saw in the case for bound states that EI is less than EI plus 1, and that's strictly less than. That means there's a gap between EI and EI plus 1. That can't occur when we have continuous solutions. Okay? And the reason why it occurs, one of the ways that you can think about it is that it comes from the canonical commutation relation. If you look carefully at the operators, remember we can always write the Hamiltonian as a p squared over 2m plus some potential. So our HI we can write as p squared over 2m plus VI auxiliary of x. And then if we look at the fact that HI plus 1 is AI dagger plus EI, and HI was AI dagger AI plus EI, you can see that the difference between those is the commutator between those raising and lowering operators. And that ends up being a commutator between p hat and wi of ki prime x, and there's some constants in front. And so that's a new potential, and that new potential has a higher energy for its ground state. It's not easy to see that it has a higher energy just from this commutation relation, but it does have a higher energy from the way that we constructed it. So we can think of this discrete increase in energy simply arising from the fact that that commutator is not zero. You see, if that commutator was zero, then it would have the same potential, and then, of course, the energy of the ground state is exactly the same. So the fact that the potential changes is the reason why the energy is bigger, and that all comes back down to the fact that our canonical commutation relation is non-zero. All right. Now, for the continuum solutions, the energy levels change continuously. And as I said, that means we cannot have a factorization chain. And instead, what we do is we just do a single factorization that depends on some parameter. This is what we use for the particle on a circle, and then we optimize the parameter to satisfy the boundary condition. And for the particle in a circle, we actually had two independent factorizations. Remember, I said factorization doesn't need to be unique. So the continuum problems are solved by taking the Hamiltonian and rewriting it as a dagger of k, a of k plus e of k, where k is some parameter that varies continuously, and then the e of k will also vary continuously with that parameter. The factorization depends on a parameter k, and we can actually write the raising and lowering operators in the same way as we did with a real superpotential. Again, it has to be real because there's no linear terms in momentum. And the key difference is that all of these e of k's must be larger than the maximal bound state energies. And you might be surprised, but this is what comes out. It means that you actually have to find a completely different factorization to solve these problems. All right, we're up to our conclusions. What we have established is that these rules all follow in simple fashions from one from another. We just use some simple logic and reasoning and a little bit of algebra. We're going to use them a lot in class, so you might want to make a list of them and refer to them as we develop them further. In the next lecture, we're going to revisit the simple harmonic oscillator, the particle on a circle, and we're going to introduce the particle in a box. And we're going to solve those problems for you within this factorization method scheme. We're also going to develop this method further as we use it to solve a number of different problems. Isotropic harmonic oscillator, hydrogen, and some more problems as well. Particles in a box and so forth. And so that then leads me to the end of this lecture. That is the end of lecture 3 of module 7.